Okay, so let's do solutions to the simple harmonic motion homework for practice set 1. This will cover problems 1 through 4. I'll do a separate tutorial for the rest of the problem set. Okay, so the first problem, we have a force is given, we stretch it a certain distance, so this is x, and attached to the string we have a mass. Okay, so we want to know what's the initial acceleration. Well, the acceleration is going to come from the force that was needed to stretch the spring. It's really just a Hooke's law force, but the second law says basically that A is going to be F over M. Okay, now the fact that it's stretched horizontally is important. It means gravity is not going to come into play because it's offset by the normal force. So we just plug in the numbers for each. 60 newtons divided by 2 kilograms. And we have 30 meters per second squared. Okay, so just a reminder of some of the basics with that. We could ask what's the spring constant. You could do F equals kx, but that may come up later. All right, what's the kitty cat's maximum velocity? So what we want to understand for simple harmonic motion, especially when they ask for velocity, that is an energy issue. And we start off when we stretch it with elastic potential, and then when we release it, it goes into less elastic potential and then also into kinetic. Since we want maximum velocity, that implies that the new elastic potential is going to be 0. So this becomes 1/2 K, I'm going to put an A in here to be consistent, so that's the maximum distance stretch, that's the amplitude, equals 1/2 mv squared. Now if you go to your notes, you'll have an equation that says V max equals A times radical K over M. Well, that's true. That comes from this setup, so it's very, very important that you understand how to do that because you will not see this equation in your reference tables. Okay, so let me make sure I've got that right. And when you plug in numbers, and I don't have a lot of space for that right now, okay, you should get an answer of 3.62 meters per second. Okay, and that's in the homework sheet. Then we can ask what's speed elsewhere. So this is a more general form, and if you set it up like I have right there, okay, then rather than just going to your notes and looking up the equation for that, you could do that, but you're not going to be able to do that on a test. Again, we start off with a certain maximum amount of potential, 1/2 Ka squared equals, and we've gone into some kinetics, so I'm just going to jump into 1/2 mv squared. So that's what we're looking for, that v, it's not the maximum, plus whatever is left over because we're still stretched some distance, and that's 1/2 kx squared. Okay, so in the notes we already solved for this algebraically, so I'm going to do it all in one step. You can plug in numbers here if you wanted to. That really is nothing more than V max, I'm just going to put an M for max, times radical 1 minus x squared over a squared. You don't have to do this equation. You can solve it like you normally would and as you've done before. All right, we're just reminding you how that comes into play. So that's going to be 3.13 meters per second. So note that that's less than our maximum speed, as we'd expect, because it's at a non-zero x. All right, and lastly, what's the period of oscillation? So that's where we use equation where we derived in the notes. That's going to be 2 pi radical m over k. Whoops, sorry. Okay. And you can plug in the numbers. This is pretty straightforward, and we get 0.76 seconds. And lastly, by what factor would the period change if the mass was halved? So this is a proportion, so basically we know that t is proportional to radical m. So our new period, t prime, is going to be proportional to what we changed it by. Well, what do we change it by? We changed it by 1/2, so it's 1/2 m, that's all under the radical sign. So that basically becomes t prime is going to be equal to 1 over radical 2 times the original, which is equivalent to radical 2 over 2. So I think I have that in the answer key. Okay, so let's move on to another problem. So this first problem is a pretty basic one, just to get you to understand some of the key things from the tutorial. All right, we have a mass two masses, a bullet and a block, so we have a collision. Looks like it's inelastic. We're given a K value and we compress this 0.34 meters, so that's X. So what's the period of the bullet block? Okay, so again, that sounds like the same equation we just did in the previous problem. T is going to be equal to 2 pi radical m. Now it's 2m, so I'm going to put an m plus m because we have the block and the bullet. Sorry, I'll put a 2 there, all over k. Numbers are given. All right, there's no conversions we have to do. Everything's in standard units. So 0.40 seconds. All right. Now, based on a compression distance, so that bullet came in with a certain amount of energy, kinetic energy, it compressed it, and what was the initial speed? So the idea is this is conservation of energy after the collision. Okay, so we have KE, all right, of the bullet slash block, right, goes into, because it compresses spring, right, elastic potential. So it's the reverse of the problem from above. So if I put in the equations, right, of course, 1/2 mv squared equals 1/2 k a squared, because that's the maximum compression distance. You put x squared, that's fine. And I go over here and I solve for v. Okay, I get k a squared all over m. Okay, and the m is the sum of both masses because this is after the collision. So put in the numbers and we get 5.34 meters per second. All right, and then we can now ask what must have been the initial speed of the bullet. Okay, so the bullet slash block moved off with the speed we found right here, and then compressed the spring. And then before it was hit, all the speed was with the bullet. So this is a conservation of momentum for an inelastic collision. So we should be hopefully comfortable with that. And we threw that in here just to remind you that that's still fair game. So basically we start off with sigma p equals sigma, sorry about that, prime. Sigma p is all in the bullet. So I'm just going to put its mass, 0.025, times its initial velocity. That's what we're looking for. Okay, the block was not moving initially, so there's no initial momentum for it, equals the sum of the two, so they combine, so the total mass is 2.025 kilograms, times the velocity of both after, which we just found here, so that's 5.34 meters per second, and do simple algebra, and we get about 433 meters per second. Okay. Moving on. Now we're going to look at some graphs. So again, we have a mass, we have a k value, and we have a distance, and it's horizontal, somewhere it says there, right? And there's our x. Okay, so calculate the period and the maximum speed. So we've done that. T again is 2 pi radical m over k. Plug in the numbers. Whoops. And we get 1/2 second. All right, 0.50 seconds. And Vmax comes from potential going into kinetic. Solve for V. And of course, we get the same equation we've seen again in prior problems. Ka squared all over m. Okay, plug in numbers and we get in 1.25 meters per second. All right, so now let's look at how each changes, how velocity changes with displacement. We did that in notes, and time, which we'll develop more later. So we're going to work this out. So the velocity, or the x, goes between two extremes, okay? And that's right here, the 0.1. So it goes to 0.1, that's really an amplitude, and then as it swings back and forth, it'll go to negative 0.1. Okay, so it's found nowhere else but between these two positions. All right, we should be able to deduce when it's fully stretched, when A is at a maximum, we have all potential, 0 kinetic, so we're going to have 0 there. And then we know that the maximum V is going to occur when V is 0, so it's going to be somewhere up here. It's arbitrary, but that we know is 1.25 meters per second. Now the question is, how do we connect those three dots? Is it linear or nonlinear? This going back to the notes, or actually to the equation, okay, we see that V is proportional to square root of A squared. Well, that's the same as V is proportional to A. So we have a linear change. So this is going to go up linearly, and then it's going to go down linearly. All right, so pretty straightforward, but again, that equation makes it clear for us. We don't have to guess. Now, in terms of time, all right, in the notes we said when we come to time, this is not going to be linear, it's going to be sinusoidal. So we're going to have to work out various points. And I want you to do it as fractions or multiples of the period. So the period is a half a second, but we don't have to actually plug in numbers for that. So let's just start here at 0, and then let's go out to roughly here. Let's call it t over 2, half the period. Let's go out to here to the full period, and then let's do marks halfway between. All right, so let's see what we can figure out. So we've stretched the spring and we're releasing it. So that implies its initial speed is 0. Okay, we're going to take it, that's going to move in the positive direction. We could say it initially moves in the negative direction, but that's okay. It doesn't matter which one we choose. So when it gets to the 0 position for x, right, then we know the speed is at a maximum. That occurs at the quarter of the full cycle. So we're going to be somewhere up here, and we know that's 1.25. Then it swings back. Okay, so in other words, we started here, 0 speed. Here is t over 4 right there, if we were, this is a time axis. And now we're back over to here, where we're back to 0. And then we head back this way time-wise, and we're now in another maximum, but in the opposite direction. And then after a full period, we're back to where we started, which is 0 speed. So that should be a nice sine curve. Doesn't look like it. Not too bad. And that's how we developed that. Okay, let's finish the last problem within our 15 minutes. That would be great. So now we have a pendulum. Okay, a pendulum, if the angle is small, that's really important, is a simple harmonic oscillator, and it has its own equation. Period of a pendulum is 2 pi radical L over G. Okay, so let's say we wanted to build a clock with this. We want that clock, the pendulum clock, to oscillate for 1 second. We want to know what the length would be. So it's very easy to make an algebraic mistake with this. So I'm going to do the algebra first, and we're going to plug in the numbers. So the smartest thing to do is square both sides. So this becomes t squared equals, and I'm going to square the 2 pi and just call it 4 pi squared. And common mistake is to call that 2 pi squared and forget the square the 2 times L over G. So do the algebra, and we see that L equals gt squared all over 4 pi squared. Now, the most common mistake I see is not right now where kids plug in a calculator, they put in 4 pi squared incorrectly. They do divided by 4 pi squared and forget to put the parentheses there, so you'll get the wrong answer. So the correct answer is 0.25 meters. Okay, if you get 2.5 meters, you've done something wrong, but it looks like it's supposed to be the right answer when it's not. So it's roughly 25 centimeters. Then let's say we bring this pendulum into a 0G plane where we can alter the field of gravity. So the gravitational acceleration goes up by 2-fold. So since G is in the denominator, we expect the period to go down if the G goes up. So if I solve for T here, okay, we already know that the period is 1 second, so we could say doubling the G, we're going to go up by a factor, or go down by a factor of 1 over radical 2. Or you can just do this by simple algebra. Okay, so this is going to be equal to 2 pi, right, 0.25 all over 2 times 9.8. Right, do the math and you get 0.71 seconds. Okay, so it's shorter because gravity is stronger and it gives us a greater restoring force. Okay, ask any questions on Schoology if anything that makes sense.